This is a slightly harder problem, a worked example from an old IBHL exam, but still good practice for you SL students. Doesn't matter if you're in the AI or AA track, this is still going to be super helpful for you to learn how to work with asymptotes, how to work with domain and ranges, weird inverse functions. So let's do it together. We got a function. F of x is equal to 3x over x minus 2. First part of this question is asking us to sketch the graph of of f of x, indicating any asymptotes and intersects. Okay, so let's first figure out what the asymptotes are and the intersects, then we're going to start sketching it. Now, the easiest one is always going to be the vertical asymptote, because again, that's always going to be linked to the domain. If the x domain is already given to us that x does not equal -2, because that would make the denominator for that fraction 0, then the vertical asymptote is literally just going to be x is equal to 2. Bang. Now the horizontal one, a little bit trickier, but not too bad. The horizontal one, we have to look at the ratio. We have to look at the x variable in the top and bottom of the fraction and look at to see whether their powers are the same or they differ. In this case, they're both raised to the first power, so they're the same, which means that the horizontal asymptote is going to be, or the equation for the horizontal asymptote is going to be a ratio of the coefficient of the x variable on top to the coefficient of the x variable on the bottom, which is 3 over 1, which is just 3. So there are the equations for our asymptotes. Oh, it's going a little crazy for me. There we go. That's a little ugly, but we're going to work with it. All right, now we need to note any intersections. Okay. To find intersects, we have a y-intersect and an x-intersect. Okay. The x-intersect is maybe the easiest one, or in this case, pretty straightforward. The x-intersect is the same thing as saying the roots. And to figure this out, we can figure it out by setting the f of x equal to 0 and then solving for whatever x value would make that function or equation true. Well, if we rewrite the function, f of x is equal to 3x over x minus 2. If we set it equal to 0, the only way that that's going to be true is when the numerator, 3 of x, is equal to 0. And the only way that that's true is when x is equal to 0, which means that the x-intercept is 0, 0. And in this case, well, we also know that this is also going to be the y-intercept, because there's no way that a function is going to cross the origin, that's the middle part where the axes meet, and not cross or only cross one of the two axes. So only for this example, not always, but only in this case, this happens to be the x-intercept and also the y-intercept. Okay, so we've got all of our intercepts down. We have all of our asymptotes down. Now we can sketch. I'm going to draw a set of axes here. There we go. And let's start labeling some stuff. We know that the vertical asymptote happens at x is equal to 2. So I'm just going to plug in a 2 here. And we denote the asymptotes with these little dotted lines usually. Vertical asymptote is in there. The horizontal asymptote happens at y is equal to 3. So I'm going to plug in 3 and add some dotted lines in there. And we also know that this curve must go through the point 0, 0. That's our x and y intercept. Okay, now we can sketch this curve. To sketch it, we literally only have to see, okay, well, what happens when x is going to be, basically just have to figure out how does this curvature line up with these intercepts. And in this particular case, we know that when x is going to be equal to, when x gets really, really, really negative, it's eventually going to approximate that horizontal asymptote. So we draw this kind of shape in here. When x is closer to that 2 range, though, the denominator of this fraction is going to be pretty small. And so we're going to see really, really big values, in this case in the negative direction. And generally when you have these kind of curves, the exact opposite shape occurs in the other side of the asymptotes. So what we would expect to see is something like this. This would be therefore the sketch for this function. We approximate our asymptotes, the horizontal asymptotes, as x gets really big in both directions, and we approximate the vertical asymptotes as they kind of intersect or come towards each other. Part B, here we go. Let's find an expression for the inverse of f of x, inverse of this function. If we remember from our previous videos, same steps we're going to take. We're first going to rewrite this function as an equation. I'll write y is equal to 3x over x minus 2. And then I'm going to switch the x's and the y's. So I'll write this as x is equal to 3y over y minus 2. And from there, nice and simple, we're just going to solve this equation for y. First thing we do is we multiply both sides of this equation by y minus 2. That cancels out those on the right side. So we end up with x times y minus 2. I'm not going to distribute it quite yet. Is equal to 3y. Now we see actually, yeah, distributing it would be the best idea. So I'll distribute it in this next step. And if we go up here, we end up with xy minus 2x is equal to 3y. Now let's move all the y's on the same side and all the other junk onto the other side. So xy minus 3y is equal to 2x. I'm literally just flipping these two across the equation sign. From here, we can factor out a y term that both of those have in common. We're left with an x minus 3 is equal to 2x. Nothing changes on the right side. And the last step, if we just divide everything by x minus 3, y is equal to 2x over x minus 3. And that is our inverse function f of x. And there, 4 points in the bag. I ran out of room, so for part C, we're moving over here. So we have a brand new whiteboard to work with, but I've copied down the inverse function that we figured out from part B of this equation, okay? So we have that answer because we're gonna need it for part C when it's asking us to find all values of x for which the original f of x function is equal to the inverse function. This is pretty straightforward as well. All we're gonna do is we're gonna set our inverse function equal to our original function and solve for x. See, well, a little bit of algebraic manipulation to see which x values would hold this true. So for this, let's multiply both sides of the equation by, or cross multiply both sides of these equations. So we end up with a 2x times x minus 2 is equal to 3x x minus 3. I'm going to distribute both of those leading x terms on both of those products. So I'll end up with a 2x squared minus 4x is equal to 3x squared minus 9x. Okay, now we got to put everything together. It's going to be important. I'm going to move everything over to this side. I think that'll make my life a little bit easier. So I end up with, I'm going to leave 0 terms on that left side. 3x squared minus 2x squared leaves me with just an x squared. And negative 9x plus 4x leaves me with a negative 5x. What I see here, don't go just dividing stuff around by x to make your life easier. In this case, it's really important that we try to keep all of our variables intact. Otherwise, we might lose some trivial solutions. That basically means we might lose some solutions that are like more obvious ones, like x is 0 and x is 1. We want to try to refrain from canceling x's out as much as possible. So in this case, we have this expression. I am going to factor out an x term since both of those terms have an x in, at least one x in it. I'm left with an x times x minus 5. And if that's equal to 0, the only way that that's true is when the first term or the second term is equal to 0. Something times something is 0. One of them has to be equal to 0. It's one of the really nice properties that we learn in our algebra classes. That means that for this to be true, x has to be equal to 0 is the first kind of step, or x minus 5 is equal to 0. X has to be equal to 5. Only in those two cases or those two solutions will that product be equal to 0, which means that only for those two values of x will the two functions in the inverse function be equal to each other. In fact, let me write this over here because I think my face is blocking it from that video. There we go. So there, that's better. x is 0, x is equal to 5. Only those two solutions hold to make the function equal to the inverse function.